Hello everyone, Professor Havens here, and I wanted to start off this video by talking a little bit about how my lectures are typically going to work online, and then we'll just get right into the first section. So as you can see, when you're in each lecture module, at the top there are going to be some resources. And those resources are the things that I'm going to be using in the videos for this chapter. So if you're ever wondering, okay, what are you using? Where are you getting your math problems from or whatever, it should all be there. And you can download them or print them out or whatever you feel like you need to go along with those lectures. Typically what I do during live class session is I provide the notes or the slides or both or whatever I think the students need to you guys, and you can work on them from there. And I also recommend that you, if you are printing them out, to keep them in a 3-ring binder or whatever you're using to organize all your notes. That way you have them all in one place and kind of have a collected set of resources. And as you're working on the online homework, and also as you're working on the activity with your group in class time, you will keep it all in the same place. That way have it all together, and if you ever need to go back and look up something, you know where it is. And additionally, as you're watching the videos, the other thing I recommend doing is, as well as taking notes and trying to do math alongside with me, to also work on the homework simultaneously. So as you're working and watching the videos from, say, for example, section 1, you can go into my math lab into the homework and work on that same homework assignment at the same time. And that way you're kind of testing yourself, seeing, okay, do I understand this or not? And sometimes, like in this particular, for the first week or two, we're going to be doing a lot of review of elementary algebra, which I'm sure most of you guys have a lot of it down pretty well. So you might not necessarily need to watch all the videos in great detail, but again, it's up to you to, watch them and keep up. But if you're working through all the homework and you're feeling good, that's how you know that you're on the right track. Also, the due dates for those are found in my math lab. I'll try to keep you guys informed, but please do check on those. Typically, they'll be due. They're not due the same day as they're assigned. So I'm giving you some time to work on them. So, like for example, this lecture, my goal is that you're working on it on Thursday for the second part of class. But not everything is due exactly that Thursday, so I'll typically give you a little bit of time. But notice that the first few assignments are due before class on Tuesday at 9 a.m. So the timing can sometimes be a little strange, but usually if I have a deadline like that means that I want you guys to be definitely done with this by the time we have class. Because if you might be very lost if you're not done with it at the time. Anyways, let's get into the first section. And anyways, chapter 1 is a lot of review on elementary algebra. I think I said that already, but if not, there it is again. So the first section is on linear equations of one variable. And I'm assuming that you guys all have a pretty good grasp of this, but I wanted to review some of the basics and also really focus on a lot of the terminology, because that's some of the stuff you might not remember. And I also I might say a lot of things, and I want to make sure that we're all on the same page and knowing what that means. So basically, a linear equation in one variable is just a more straightforward equation, an equation that has a singular variable without any exponents or anything, and an equal sign, and whatever other math it contains. But typically just your basic operations, adding, subtracting, multiplying, and dividing, without anything more complicated than that. And to solve simple equations like that, we're always going to be using the additive or multiplicative property of equality, which is basically, as you've probably heard before, is doing the same thing to both sides. So like, for example, in an equation like x plus 17 equal 54, the goal would be to do something to both sides of the equation in order to solve for x, the typical goal of an equation. And also, just not to get too big of a sidetrack here, but I wanted to remind you about what is the purpose of these sorts of equations and why do we care about them. But remembering the main point of algebra is to try to design an equation that will relate to actually something real. And then we can use all of the mathematical properties of algebra to actually solve that equation, and in so doing we could actually solve a more difficult problem. And in a lot of higher level math and science, the types of problems that we're solving are much too difficult to solve without actually having the math, without having a mathematical equation. And obviously one of the main points of college algebra is to learn the necessary functions and equation solving set to be able to work in the sciences. Well, at least the basic on a basic level. But anyways, so all that said and done, what we could do is subtract 17 from both sides of the equation, and by doing that, plus 17 and minus 17, because those are what are called additive inverses, will cancel each other out and make 0. And what we'll be left with is, you could say x plus 0, or just x, is equal to, well, 54 minus 17 would be 37. And basically we could come up with the answer, or what does x equal, or if I could translate this equation back to what I was saying before, what does this equation stand for? Well, a lot of times in algebra we're just designing practice problems. They're not necessarily anything real. But we could imagine what this equation could represent, where x is always, or is the typical variable, but we might use any letter to stand for an unknown, something we don't know usually, or assigning it to be a letter for something real that it might represent. But in this case, I could invent a real problem that might correspond to this sort of equation, which might be, well, if Javier had some number of tennis balls, and then he found 17 more tennis balls, and after he'd found 17 more tennis balls, he had acquired a total number of 54 tennis balls. How many did he start with? Because notice, if you rewind and listen to that problem I just invented, I said he started with some number of tennis balls. He didn't count them before. Then he found 17, which I guess he counted, and now he has a total of 54. We could then backtrack and figure out, well, how many did he start with? Of course, you could take, well, he ended up with 54, subtract 17, because that's the number that was added to it, and that makes sense to figure out, well, how many tennis balls did he start with? Javier started with 37. But a lot of times I'm not going to invent a context like that to represent an equation, because it's elaborate, and then I have to come up with some crazy scenario that represents it. So a lot of times we don't focus on the what does this mean, but we can kind of see, well, how do I reverse engineer this? And that's exactly what we're doing when we subtract 17, is we're trying to figure out, well, what's the opposite of adding 17 to come up with, well, what would the x be all by itself? And returning to that property I mentioned, which is called the additive property of equality, is usually what it's called, not addition, but it doesn't really matter. It's a property within any mathematical equation, which is basically we're allowed to add or subtract the same quantity from both sides. And it's kind of like an equation is representing a true mathematical statement. And the assumption is that this is equal to this. If we're writing an equation to begin with, the assumption is, yes, this is always equal. And you typically wouldn't write a false equation like this, 4 is equal to 2, because that usually defeats the purpose of an equation, though there are some times where those sorts of things are relevant. But anyways, but the idea is, if this original equation is the thing I'm trying to figure out, if I do the same thing to both sides, like say for example I add 5 to this side, if I add 5 to the other side, it will remain true. If I only do it to one side, that equation's not going to be balanced because they're not going to be equal anymore. Or in the same way, if I subtract 17 from both sides, it should still be equal, and this equation should still be true. And the same goes for multiplying and dividing. If you multiply both sides by 2 or divide both sides by 2, or whatever number you want, besides you can't divide by 0, and we might review that idea later, it's still cool. And then reviewing one other basic aspect of an equation, which is checking your solution. So additionally, after all is said and done and I find the answer, which usually means getting x by itself and figuring out the answer to the equation, you can always verify, okay, does this answer make sense, by plugging it back into the original equation. And really this is a check to make sure when I was doing algebra, when I was doing stuff to both sides, whatever it was I was doing, did I mess it up or not? And in this case, if I substitute 37 back in for x, 37 plus 17 is indeed 54. So I could, verify, check that out. And that, we usually, how I'm going to refer to that is check my answer, verify my solution, something like that. And in the next couple videos, we're going to review a few extra steps, because these first few examples are some very basic ones. And one other thing I wanted to review about fractions is if you have a fraction multiplied to a variable and you want to cancel out the fraction, again, the goal of an equation to solve is always to get the x by itself. And this is how I like to think about it. I want to get that all by itself. So my goal is to cancel everything else out or delete it or remove it. How do I do that? Is one of the things in algebra. It really depends on the context. There's a lot of different situations and a lot of different rules you would apply in each case. But when it comes to a fraction, multiplying by the reciprocal, and really it's because 1/7 is being multiplied to x. And technically, like, say for example, in the equation right next to it to the left, 15y is equal to 195, the opposite of multiplying is dividing. So in an equation where multiplication occurs, we always want to do the opposite. Like over here, when I had plus, I wanted to do minus. Or if I had minus, I want to do plus. It's because the opposite operation performs a cancellation and leaves us with 0. And so with multiplying by 15, if you then divide by 15, 15 divided by 15 leaves us with 1 or 1y. And that's just a single y all by itself, which is why we often write it like this. 15 divided by 15 cancels, but you got to make sure you're using the correct operation, right? Because I don't want to subtract 15 in this case, because 15 times y minus 15 isn't going to cancel. 15 times y divided by 15 will. And so that's why you got to be careful. And of course, I always want to do the same thing to both sides. So using that additive or multiplicative property of equality. And technically this is multiplicative because multiplying and dividing are really the same thing. They're just opposites. And so if you're wondering, well, is there a divisive property of equality? I guess. But anyways, technicality that's not worth going into. And also, as we work through the semester, I'm going to teach you how to use a calculator. So in the syllabus, I've marked the TI-84 as required. Since we're online, it doesn't really necessarily matter which calculator you're using, and you can often just use an internet calculator of some kind. But in a typical class, like say for example, you need to go take calculus, your professor is not going to let you use your computer and use a computer calculator to solve math problems. So I think it's important to learn how to use a calculator that most professors allow you to use, like the TI-84 or whatever. This is a calculator that I let all my students use. So that being said, I'm going to use it a lot, is my point, in these lectures, and I'm going to teach you how to use it. But if you don't necessarily know your basic arithmetic off the top of your head, you could always use a calculator. And in this case, I'm just going to have it off to the screen up there. And yeah, going to try to show you how to use it. But for when we get into graphing and more complicated algebraic stuff, and I'll try to teach you what the calculator can and can't do. But in this case, anyways, we could again verify by saying, well, 15 times what is equal to 195? 15 times 13 is 195. Cool. And we're sort of reverse engineering the problem by, well, if I want to know 15 times what makes 195, I could just divide 195 by 15, and that will tell me exactly what I need to know. But getting back to the fraction example, which is the thing I wanted to do last, and it looks like I forgot to finish this first example over here. Add 42 to both sides, what I end up with 78. And you don't have to necessarily leave the variable on the left-hand side. What I typically like to do is I like to circle my final answer, and that's something that when you're doing work on a test by hand, something I recommend doing. You don't necessarily have to, but it just kind of helps you or me or the grader know what is your, what's your final conclusion after all is said and done. Another thing you might be wondering is, do I have to show these steps? Because a lot of you might be able to do this sort of math in your head. I definitely can. And as we get further into the semester, this is math I'm not necessarily going to show every little step. But you know, for the purposes of reviewing the more basic stuff, I think it's good, and I will. But no, you don't need to show the really basic stuff like this. I wouldn't typically do it myself. But just for the purposes of reviewing is why I'm being so detailed. But getting back to my original point about fractions, to get rid of a fraction, and this is probably a trick you remember, is usually what you do is you multiply by the reciprocal in order to cancel a fraction, which 1/7, what we do is usually multiply by 7. Or you might remember, you know, them saying multiply by the denominator or the LCD or whatever. So I would do the same thing to both sides again, because I can't just do it to one side. And that would leave me a cancellation of 7 and 7, which would be x equal to 14. But this is actually using the same rule, because technically 7 and 1/7 are what are called multiplicative inverses or reciprocal fractions. Because if you flip them over, 7 over 1 is just equal to 7. Reciprocal fractions always cancel, because really that's what it happens when you divide by a fraction. So just, you know, reviewing rules for dividing fractions. Oops, I accidentally erased my equation. 1/7 x. If we were, because 1/7 is multiplied by x, technically we could just divide both sides by 1/7, and that would cancel, because as I said right over here, right, if I multiply, well, how do I cancel? I divide. And anyways, but it's a shortcut, because if we divide by 1/7, right, the rule is, well, you flip and multiply. I multiply by 7 over 1, aka the reciprocal fraction. And if I'm doing the same thing to both sides, I'm dividing the other side by 1/7 as well. So really what I have is 2 divided by 1/7, which is just 2 times 7 based on flip and multiply. So it's like using a rule of fractions as a shortcut or a trick. Anyways, what we end up with is x equal to 14, of course, because 1/7 of 14 is indeed 2.